What is a gradient vector? Good question. It's a vector, right? I know it sounds like a dumb answer, but it is a vector. So, right. So what does gradient mean? I don't actually know. I mean, let's look it up. What does gradient mean? Right, I do too. Like you think of like the thing where like you have the colors that kind of just merge into the next, like it's very much like a. So according to Wikipedia, the gradient, where'd you go? That's called a nabla. Interesting. I had no idea. I mean, it's the words I've said many times. Wow, that's a lot of words. I wanted to give you something other than just what I've been saying, though. I mean, no, the gradient really is, it's a vector and it points in the direction of greatest change. But like, so like, okay, I feel like that's not great, right? I mean, so let's see what the Googles can tell us. What is the meaning of the gradient?
Is it possible to make one big problem where it's actually find gradient vector and then find like the general solution? Like, could you put this?
So I would say, so when you say general solution, I feel like you're talking about the stuff we've been doing very recently, and that's not really related to the gradient so much. So here's what I would say. This general solution stuff we just been talking about, where we're talking about systems of linear differential equations. We are talking about taking some system of linear differential equations and finding the functions that are solutions to that, x of t and y of t, typically. Whereas when you're talking about a gradient, I would say it has a much more physical interpretation. So a gradient is more like you've got a surface, a mountain, a saddle, a thing, right, out that you could walk on, you could hike on. And the idea of the gradient is if you're on the mountain, what direction could you walk in that would get you up the mountain the fastest? Right, what direction is the steepest? Exactly. So they're kind of two, although they seem like they could be kind of related, they're not really related. Yeah, let me see one more thing here. You mean the stuff I've been talking about, the tau and the delta, the trace? So that's that's a way of talking about, I should get some pens here. That's a way of finding the eigenvalues of a matrix more easily debatable. So just to kind of remind you, and again, you should probably for your exam do this, whatever is the easiest way possible for you. So if your matrix, for example, looks like, I'm just gonna make something that's probably going to be terrible. If that was our matrix, first of all, if that was our matrix, what does that represent? Right, someone gives you this matrix. We know it has meaning because we've done like 100 of them, maybe not quite that many, but I could see someone asking you on an exam, like, here's like, tell me what this means. And what this really means is we're really talking about how dx dt is equal to 6x plus 2y, and how dy dt is equal to 3x minus 4y. Right? When someone gives you this 2x matrix, they're really saying, oh, we're talking about this system of linear differential equations. And then to solve it, right, to solve it, meaning to find the general solution, we find the eigenvalues. So step one, eigenvalues. Step two, eigenvectors. Step three, your solution, x of t, y of t, is equal to c1 e to the lambda 1t plus v1 plus c2 e to the lambda 2t v2. They're big steps, but they are just the same steps over and over and over again. And then I should say step four, if we have initial conditions, if we have x of 0 equal to something and y of 0 equal to something, a number and another number, then we can use those initial conditions to find C1 and C2. that C1, and that C2.
Just the stuff we did, Tuesday.
Sure. And what we've been talking about in class for a couple of weeks now, I feel like. So for this particular example, we could start off here, but they're probably going to try to be terrible. Let's take a look and see. So you could either do it by, say, finding the determinant of A minus lambda I, which is going to be 6 minus lambda, 2, 3, negative 4 minus lambda, and setting that equal to 0. The odds are pretty good. It's going to turn out to be terrible numbers because I just made it up. Let's find out. So we multiply these together. 6 minus lambda times negative 4 minus lambda minus 2 times 3. Be sure to remember the minus 2 times 3 part. I was helping someone the other day and they totally forgotten the 2 times 3 part. And so their eigenvalues were really easy to find because they were wrong, right? It was really easy to get that equal to 0 because they were just getting 6 and negative 4, but that wasn't right. So we actually multiply this out. Negative lambda times negative lambda is lambda squared. Negative 4 times negative lambda is 4 lambda. Negative lambda times 6 is 6 lambda. So I'm getting 6 lambda minus 4 lambda, which is 2 lambda. And then 6 times negative 4 is negative 24. Minus another 6 is minus 30. And the idea here is that when you find this, so this is actually not, this is a good example of something. So setting this equal to 0 and trying to solve this, it's not going to factor. There's no way I can find integer numbers that multiply with negative 30 and add positive 2. Close, but no cigar. 5 and 6 don't really work. 3 and 10 don't really work. Not going to happen. So here you would then be getting eigenvalues by using the quadratic formula. So you're going to get lambda equal to negative 2 plus or minus the square root of 2 squared minus 4 times 1 times negative 30 all over 2. So the question that we have to ask ourselves, so I should say, right, there's kind of 2 directions you can go when you do this. You can either be asked to find the general solution, which I don't really want to do for this one because they're going to be not very nice. You're going to have, I mean, we can talk about it a little bit, I guess. Maybe we will. I feel like your teacher's not going to go there. So if we simplify this a tiny bit, we end up getting negative 2 plus or minus the square root of 4 plus 4 times 30 is 120 plus 4, so 124 all over 2. You can probably simplify that more. I don't think we really need to. I mean, we could. 124, you could factor out a 4, I guess, and be left with 31. You could write this as negative 2 plus or minus the square root of 4 times 31 all over 2. Square root of 4 is 2, so you end up getting negative 2 plus or minus 2 root 31 over 2, which is negative 1 plus or minus the square root of 31. You could do that. So, eigenvalues, are they real or are they complex? So complex means you're taking the square root of what kind of thing? A negative. Are we taking the square root of a negative? No. They're not nice. And you might say they are complicated, but they're definitely not complex because they're not imaginary. They're irrational for sure, but they are definitely real numbers. And so if they're real numbers, it means we have what kind of equilibrium? Spiral or a node? It's a node for sure. Now, is our node stable or is our node unstable? It's stable because the real part is negative. I'm a liar. I'm a total liar. It's not a node. It's a node, or it's what else can it be if they're both real? It can be a stable node, an unstable node, or a source is an unstable node. Sink is a stable node. But there's one other thing that starts with an S. A saddle. It could be a saddle. And it is a saddle. Because our eigenvalues are both positive, both negative, or one positive, one negative. One positive, one negative. Right? Negative 1 minus root 31 is definitely negative. Negative 1 plus root 31 is definitely positive. Now, we would have known this if we had done it the other way, because we would have gotten the determinant that was negative, and we'd be like, oh, we have a saddle. So I just want to point out that if you had used the trace determinant method, the trace here is 6 plus -4, which is 2. And the determinant is 6 times -4 minus 2 times 3, which is -24 minus 6, which is -30. And the determinant being negative means you definitely have a saddle right off the bat. But again, your teacher probably wants you to do it this way. She should probably just do it this way. Say it one more time. I hear the what? Oh, sure. So the trace of a matrix. So I should be very, very clear. There's a trace of a matrix, which is super straightforward to find. There's also the trace, which you talked about back when we were graphing things, right? If you're talking about functions of two variables, the trace is like when you set z equal to 0 and find what's in the xy plane, you set x equal to 0, find what's in the yz plane. Like there are those traces, which is a different thing. But the trace here is just you add up whatever's on the diagonals. So 6 plus -4 is 2. That's the trace. That's a good question. So there are actually lots of things about the trace of a matrix that come up later on. But for our purposes, the trace is the following. If your eigen, so basically if you don't have a saddle, so let me break it down for you. So if you're looking at trace determinants, thing 1, if the determinant is negative, saddle. All the time, every time. If the determinant is positive, then you have some possibilities. You can either have node or spiral. In either case, if the trace is positive, it's unstable. If the trace is negative, stable. Because if you look, so basically, if you look back here, if this hadn't been the case here, where it was plus or minus this, like if it was some other smaller number, the trace is just giving you whatever's out here. So if your trace is negative, you're getting a -2 out here. Sorry, my brain is saying this backwards. So apologies. Am I saying this backwards? Am I not saying? It seems like now I feel like no, trace is positive, definitely unstable. Yeah. The problem is this is not an example. So let's look at one more example. Yeah, let's do a question there. Okay. So I would refer you back to, before I get too crazy here. I would refer you back to this picture here. Just as a reminder, which is a great kind of picture. If you look at the determinant of your matrix, if it's negative, saddle. If it's positive, you can either have a node or a spiral. And if you look here, if the trace is positive, you're in unstable land. The trace is negative, you're in stable land. So that's I mean, the trace really is just the sum of the diagonal elements of the matrix. But what I would say is the trace can tell us things about what our system looks like. So let's look at one more example, at least one more example. So for example, if we had the matrix, sure, 5, 2, make up something that's not going to come out to be, okay, 3, 7. Trace is 12. 5 plus 7. Determinant is, let's see, 5 times 7 minus 2 times 3 is 35 minus 6, which is 29, which is certainly positive. So in this case, without doing any other work, I can see that it's an unstable. I can't tell if it's a node or a spiral though. Because to tell if it's a node or a spiral, you have to compare the, you can either find the eigenvalues, or you can think about just what makes it positive or negative. I mean, makes the inside of the square root positive or negative. Meaning, if we were going to find the eigenvalues would be the trace plus or minus the square root of the trace squared minus 4 times delta over 2. But the only thing that really matters is to determine if this is going to be complex or real is what's happening right here. So you could just look at that and say, oh, the trace squared minus 4 times the determinant is 12 squared minus 4 times 29, which is 144 minus, it's going to be close. 4 times 9 is 36, 4 times 20 is 80. It's not that close. 16, which is positive. So that thing being positive means we're taking the square root of a positive number, which means our eigenvalues are real. So our eigenvalues are real, and we know that they're both going to be positive because our trace is positive. But again, what I should really be saying is this is probably not the way you want to actually be doing it. It's cool, I like it, it works, and it tells us some cool stuff, but at the end of the day, you're probably going to be expected to just find the eigenvalues in the usual sort of way. Yeah. Oh, the one on page 650? Yeah. It's a great picture. You know, can I? And I can zoom in a little more. So what do you want to say about this picture or ask about this picture?
It's just the name, the names of stuff are like that confusing me. It's like parking and measurement. Because like nodes, I'm just thinking of them as lines.
But so the nodes aren't really just lines though. The thing is nodes, because they're not going straight in to the origin or straight out. They're kind of curving and curving out. The difference is, and I've had a hard time justifying this in my brain over the years, is that a spiral is going to go around and around and around a bunch of times before you really get into the origin or away from the origin. Whereas a node isn't going to curve like back on itself more than once. It's going to just kind of curve around and then end. And here's the difference. Oh, here's a really good way of thinking about it. Spirals, they're graphs, they're phase plane graphs, whatever you call it, don't have eigenlines. Sure, no, be quiet. Here's the way to think about it. If we were gonna, so we talked about the eigenvalues so spirals have complex eigenvalues. And although we didn't find them, it is true that the eigenvector for those eigenvalues would also be complex. And so graphically, we can't really graph the complex eigenvalue because it's supposed to just be a line in this real kind of plane. So the idea is there isn't an eigenline that acts as a barrier. So let me show you what I mean. We've got some examples over here. So I'm just going to show you an example. We can work backwards from it for a second if you want, but let me just grab this example that I've got here. Yeah, sure. So this might be an example we looked at one time before. I don't recall exactly. Let me grab this here. So here's what I want to point out about this. So in this example, where we have dx dt equal to negative 3x plus 3y, dy dt equal to 6x plus 4y, you can find the eigenvalues. The eigenvalues are positive 6 and negative 5. And the associated eigenvectors are for positive 6, 1, 3, for negative 5, 3, 2. So, sorry, 3, negative 2. So here is your eigenline for lambda equal to positive 6. This pen. And green, we got green, I've got green. And this line here is the eigenline for lambda equal to negative 5. So along this line, your arrows are pointing straight in at the origin. And along this line, your arrows are pointing straight out. So here's what happens. If you say you want to have some initial condition, right? So let's say we start, well, if we start on one of these eigenlines, you're just going to be going away, 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 away. Or in this case, in. Sorry, it's not great. On the other hand, if you start somewhere else with some other initial condition, like let's say we have the initial condition. Do we have one written down here? Probably not. No, it's okay. So let's pretend we have the initial condition. I don't know. Let's say we have the initial condition. I want to do something that's kind of not too terrible to graph. Sure, let's say we have the initial condition 2, -1. So here's what you should know. Eigenlines are barriers you can't cross. Because once you're on the eigenline, you are start going in the direction of the eigenline. You cannot cross an eigenline. I'm gonna say it one more time. You can't cross an eigenline. You can move asymptotically towards it. Or yes, if you start on it, you can move on it. But unless you're already on it, you can't even get on it. You can get really, really close to it, like we usually do. So here's what's going to happen here. If I start here, I'm going to move in the direction of these arrows, like this. And now this null line, you have to cross purely vertically, because it's a dx dt null line. On this null line, dx dt is equal to 0, meaning the change in x is wholly 0. So we can't change in the x direction, so our arrow has to be totally vertical. So we're going to cross this totally vertically. And then we were moving to the left. Then we got to a place where we're moving left or right. So we're going to change the direction. Instead of moving to the left, now we're going to move to the right. So we now go this way, getting closer and closer to that eigenline. That's kind of it. So notably, and this is I want to let me actually let me look at this next one here, because I want one that actually is like this. If I have other examples, that's not. I want a knot. I want a sink. Not many sinks. So let's just say, let me just draw one for you. So let's pretend we had some. In fact, we don't have to pretend. I can make something very easily. So let's say we have this system where our matrix A is the matrix -2, 0, 5, -3. 100% going to be a sink. How do I know? What are my eigenvalues? Right. Our eigenvalues are definitely -2 and -3. And we can even find the eigenvector. We should find the eigenvectors when we talk about finding the thing I'm talking about, the eigenlines. So for lambda equals -2, we have -2, 0, 5, -3 times xy equal to -2 times xy. By the way, for everyone, if you see a matrix like this on your test, your teacher knows what they're doing. Their intention is that you don't do all the work to find the, unless they specifically say you have to do all the work. Their intention is that you are able to see that and know the eigenvalues are -2 and -3. Well, let's do the work. So if I want to find the eigenvalues, I'm going to do the determinant of A minus lambda I equal to 0. So if I do that, I have the determinant of -2 minus lambda, 0, 5, -3 minus lambda equal to 0. And the determinant of this matrix, here's the important part. Here's where we're going to see what we get. You've got -2 minus lambda times -3 minus lambda minus 0 times 5 equal to 0. Well, the 0 times 5 is just 0. So look what we're left with. -2 minus lambda times -3 minus lambda equal to 0. You could multiply this out, but you don't have to. At this point, we can see, oh yeah, lambda is going to equal -2 and lambda is going to equal -3. So that's why it happens, because whenever you have a 0 here or a 0 here, this part just becomes 0. And so you've already factored it, essentially. Yeah. The trace is so more generally for any size matrix, the trace is always the sum of the diagonal entries, meaning always from upper left to lower right. Those are not diagonal entries. The diagonal entries specifically refer to the entries where the row and column have the same number. So here I'm in the first row and first column. Here I'm in the second row and second column. So if I'm finding the trace, I'm adding up all the entries where the column and row number match. You're right, this is also feels like a diagonal. I see what you're saying, like physically, they both feel like diagonals, but the thing that we call the main diagonal is the thing that always starts from the upper left and goes down to the lower right. So for example, if you had a 3x3 matrix that looked like this, the trace would be 1 + 5 + 9, because we're adding up from upper left to lower right. So just to be clear. Yeah. So finding the eigenvalue vectors, I've got -2 times x equals -2 times x, which is no help at all. So then we do the second row, 5x - 3y equals -2y, 5x equals y, and that's my eigenline, y + 5x. My eigenvector is x is 1, y is 5. Yeah.
What is the, I don't need to, maybe I do. What is the other way to find the eigenvector? Because I always find it is.
Sure. Cool question. So the other way to do it is to take your matrix and subtract your eigenvalue from each entry. So I'm going to do -2 minus -2. Sorry, from each diagonal entry. So I'm doing a minus lambda. So -2 minus -2, 0, 5, -3 minus -2 times the eigenvector equals 0, 0. That's the other way to do it. And so if we do that, we've got -2 + 2, which is 0. So I really got the matrix 0, 0, 5, -3 + 2 is -1 times x, y equal to 0, 0. And so then you've got 5x minus y equal to 0, and you get 5x equal to y, which is the same thing we got over there. So it's the same, it ends up being the same answer. The reason most of us, at least in the AATC, like to talk about this is because the real meaning behind what an eigenvector is it's a matrix that when you multiply, it's a vector that when you multiply the matrix by it, you get a multiple of that vector. And so writing it this way is more true to the nature of what an eigenvector is. But as we said last class, I think, if your eigenvalues are not so nice, like irrational, then doing it this way is often an easier calculation to do. But either way is totally fine. And your teacher should be accepting of doing it that way. So, yeah.
Why is the vector 1,
So the reason because I picked something. So remember the vector is x, y, right? X, y. So pick a number for x. I'm going to pick 1. If x is 1, what's y have to be? Right.
Doesn't matter what we choose as.
The only thing you can't choose is 0. You could choose x equal to 2 and get y equal to 10. Or x equal to 3 and get y equal to 2. Because anything that's a multiple of an eigenvector is also an eigenvector. Standard choice is usually picking things to be, typically we make the choice so that everything is the smallest possible integer. That's what we usually do. But yeah. So another way to think about it is if you graph the line y equals 5x, this point 1, 5 should be on that line. And it is. If x is 1, y is 5. Yeah. Next question. Right. What it really means is this doesn't tell us anything. This isn't saying x equals 2 or y equals, right? It's just giving us, well, any value of x works there. If x is 2, -4 equals -4. If x is 3, -6, right? It doesn't give us any information. So if the first equation doesn't give you any results, then we look at the second equation. And I will tell you, that sort of situation is always going to happen if you have a 0 here or a 0 here. So whenever you're in this nice situation where it's really easy to see the eigenvalues, you're also going to have the situation where you have this kind of non-information result here, which is fine. Let's find the other eigenvector. So that was for lambda equal to -2. Let's do lambda equal to -3. Which way should I do it? The first way or the second way? Okay, let's do it the first way. So got -2, 0, 5, -3 times xy equals -3 times xy. And let's see. So the first equation now actually does tell me something, even though it looks like it might not. I've got -2x plus 0y equal to -3x. And that tells me that x has to be 0. There is no other choice. If you don't like just seeing it there, you can add 3x to both sides. So I add 3x, I get x on the left and 0 on the right. Oh, x equals 0. And the thing here is that using the other equation won't tell you anything different. If I use the other equation, I get 5x minus 3y equals -3y. The -3y's cancel, and you're left with 5x equal to 0, which still gives you x equal to 0. Yeah. So either case, x equals 0. And then, of course, when one of the components is 0, the other component can be anything. And we usually choose 1. Okay. So let's draw this thing. Oh, I'm gonna draw my eigenlines too, but first let's, or I'm gonna draw my null lines too. But first, let's draw the eigenlines. So ruler. Cool. So let's see. My eigenlines were, or my eigenvectors were 0, 1. 0, 1 just means that my eigenline is going to be this line here because I'm going up to the point 0, 1. And then my line is that. So here's my eigenline for lambda equal to -3, which was lambda 2, and v2 equals 0, 1. And since my eigenvalue is negative, which way are my arrows going to point? The possible answers you can say are inward or outward. Inward. If the eigenvalues are negative, the arrows point towards the origin. So they're not just down or up, right? They're literally pointing towards the origin. So on this part of the eigenline, pointing towards the origin, and on this part of the eigenline, pointing towards the origin. Okay, my other eigenline is the line that goes to the point 1, 5, which is not, I'm going to draw it a little exaggerated or less or not as steep, just to make it so it's easier to see what's happening here. So here's my other eigenline. Along the line y equals 5x, which goes with the eigenvalue lambda equals -2, which goes with the eigenvector 1, 5. And there, my eigenvalue is also negative, so I'm still pointing inward. Okay, let's talk about the null lines for just a second. So I'll remind you all, the null lines you just get by setting each of your differential equations equal to 0. Now, we didn't write the differential equations. That doesn't mean we don't know what they are. Our first differential equation comes from the first row of this matrix. So we're just saying, oh, okay, that's going to be dx dt equal to -2x plus 0y. So if we set that equal to 0, because that's how you find the null lines, by setting each thing equal to 0, what are we going to get? X equals 0, which already happens to be one of our eigenvectors. Again, that doesn't usually happen, but it does always happen when you're in this case where one of your upper or lower corners is a 0. So that's this line right here. So this is my dx dt equal to 0 null line. And then my other null line we get by setting the other equation. dy dt equal to 5x minus 3y equal to 0. If I want to graph that, I'm going to solve for y. So 5x equals 3y, y equals 5/3 x. So not quite as steep as this line here, right? Because this is the line y equals 5x, but still, moderately steep. Again, I'm going to draw a little not as steep as it actually would be because it's just easier to see things if we draw them not super exaggerated. So here's my y null line. So on this line, dy dt equals 0. So what does it mean that dy dt equals 0? If dy dt equals 0, meaning there's no change in y, which way do my arrows have to point? Vertically or horizontally? Horizontally, because there's no change in y. So there can't be any up or down part. There has to be totally a horizontal part. So all my arrows along this line are going to point totally horizontally. Now, you could either test a point on them to see if they're pointing to the right or to the left, but you can see that over here, we have to be pointing to the left because right here we're pointing to the left. So these are definitely going to be going to the left. These are definitely going to be going to the right. You could also test a point though, right? If you test a point like, for example, on this line here, if you test the point, let's say 3,5, that's easy to plug in. Then at 3,5, dx dt is -2 times 3. And dy dt is, of course, 0 because it's 15 minus 15. So yeah, over here at 3,5, we're pointing to the left because dx dt is negative. And over here at, say, like -3, -5, we're pointing to the right because dx dt ends up being positive. Right, yeah. So and again, we found this line by setting dy dt equal to 0. And we found this vertical line by setting dx dt equal to 0. That's how you find the null lines. Or the zero isoclines, as they're also called. Yeah. Eric. No. So the direction for well, I mean, maybe, okay, I'll back that up a little bit. Here, you could maybe say yes, because we already knew it was going to be a stable node. Because the eigenvalues were both negative. But I'd say generally, null lines are not an in or an out. They're a purely horizontal or a purely vertical. And then you have to decide if they're up or down based on what's happening nearby. That I would say is what's really true. Okay, so now check this out. If I start, say, like over here. Well, over here, I kind of look at what two things I'm between. I'm between this and this. So I'm going left and up. So I'm going to go left and up, remembering that the black lines are barriers, right? I can't cross an eigenline. I can totally cross a null line though, unless they're the same thing, and then you can't cross it. So what's going to happen is I'm going to go left and up. I'm going to cross this purely horizontally, and then I'm going to have to go left and down. And I can't cross this eigenline, so I'm going to go left and down right there to the origin, like that. Note that it is not a spiral, right? I'm not spiraling around and around and around the origin. I'm just curving into the origin. So that's, I know that was a lot of work to say what I was trying to say, but that's kind of the idea of a node versus a spiral. Nodes, they're not straight into the origin, they can curve into the origin, but you're not going around and around and around. Whereas with a spiral, you're totally going around a few times before you actually get there. Yeah. Well, yes, generally yes. In this example, no, because it is also the eigenline. So it's usually not the case that the null line and the eigenline are the same thing, but it will always be the case that one of your null lines will be the same as your eigenline when you're in this situation where you have a 0 here or a 0 there. So in this situation, you will definitely have a null line like that. We can do another one where we don't have that situation if you like. I'm not happy to do that. Say no. Say oh. Let's do another one where things are not too terrible. Let me make up one where yeah, go ahead. Sure. Let's say that one more time.
Because I think there's like negative and like bad, so like.
Sure, I get that.
Versus like a positive value.
Right, so that's actually an excellent question. Let's talk about it. So in this situation where both my eigenvalues are negative, let's write the general solution. So the general solution would be C1 e to the lambda 1 t times V1 plus C2 e to the lambda 2 t times V2. So let's, I'm gonna write it out. I'm gonna write it as C1 e to the lambda 1 is negative 2 t times V1, which is 1, 5, plus C2 e to the lambda 2 is negative 3 t times 0, 1. And let's actually go a step further and write it how we would do maybe in a homework problem and separate them into a couple separate different pieces here. So, right, because this is really what our x of t, y of t is equal to. So I'm going to write out both pieces here. So we're going to say that, whoops, come on. We're going to say that x of t is 1 times c1 e to the negative 2t plus 0. I didn't even need to write that part. And y of t is 5 times c1 e to the negative 2t plus 1 times c2 e to the negative 3t. And so here's what I want to point out. If we take the limit as time goes on and on and on and on and on, meaning as time tends towards infinity, if we take the limit as t goes to infinity of x of t, which is the limit as t goes to infinity of c1 e to the negative 2t, what happens to e to the negative 2t as t gets really, really big? Right, that's exponential decay. If you like, and I do, I might rewrite this as the limit as t goes to infinity of 1 over, sorry, not 1 over, c sub 1 over e to the positive 2t. Now as t goes to infinity, 2 times infinity is infinity, e to the infinity is infinity, and a constant divided by infinity is super small. And in a similar way, the limit as t goes to infinity of y of t is the limit as t goes to infinity of all that stuff, 5c1 e to the negative 2t plus c2 e to the negative 3t. But since that's a negative 2t and that's a negative 3t, both those exponents are going to negative infinity, which means we're decaying. E to the negative big number is a super small number. These both go to 0. Right. So what we're saying here is, if we start here, as time goes on and on and on, right, we're moving in the direction of time moving forward. Oh, look, we have to be getting closer and closer and closer to the origin. That's why when you have negative eigenvalues, they exactly correspond to being stable, because as t gets bigger and bigger and bigger, all these things get smaller and smaller and smaller, closer and closer to 0, which is the equilibrium. So negative eigenvalues exactly correspond to a stable equilibrium. Right. Exactly. So let's look at an example of that, just so we can draw the pictures and also see things. So let's look at one more example. I'm just going to try and make something up that has nice positive eigenvalues real quick. Let's see. So I threw away that piece of paper that had cool things on it. It's fine. Let me think for just 1 second here. So I want my matrix to be, I want to have a positive trace. I think the trace fun, like let's say it's 12. And then I want the determinant to be sorry. 12. Who picked 12? Why would I pick 12? Sorry, that's not what I wanted. Apologies. I want it to be like 7. And then I want to subtract 12. Sure. Sorry, I'm almost there. I promise you. 1 sec. I have to think for a minute. Minus 1. So I need that to be a 12. And the determinant to be 12. That's gonna be 6. And I need a -2 and a +3. I think that should work out all right. Let's double check before we get too carried away though. So let's find the eigenvalues before we do anything else, just to make sure things are going to work out all right. So finding the eigenvalues, determinant of A minus lambda I, it's going to be 6 minus lambda, -2, 3, 1 minus lambda. And we said that if we do that 6 minus lambda times 1 minus lambda minus -2 times 3, which ends up giving us lambda squared minus lambda minus 6 lambda is -7 lambda plus 6 plus 6, which is lambda squared minus 7 lambda plus 12 equal to 0, which gives us lambda minus 4 times lambda minus 3. Cool. So our eigenvalues are both positive. So just from that alone, we know we're going to have an unstable node for sure. But let's do the rest of the work. So we're going to find eigenvectors. So for lambda 1 equal to 4, our eigenvector is going to be, let's see, 6, -2, 3, 1 times xy equal to 4 xy. So we've got 6x minus 2y equal to 4x. We've got -2y equal to -2x, or preferably y equal to x. So my eigenvector is 1, 1. And then for lambda 2 equal to 3, I have 6, -2, 3, 1 times xy equal to 3xy. So probably going to not be quite so nice. That's fine. We got 6x minus 2y equal to 3x. So I've got 3x equal to 2y. I often like to just stop there because then I can see that my eigenvector is, well, if x is 2, then y is 3. Or you can solve for y and say y equals 3 halves x, and then if x is 2, 3 halves times 2 gives me y equal to 3. So far, okay? Questions so far from the people on Zoom? Any questions? Any questions? From Sarah or Sarah? Sarah with an H? Sarah without an H? Okay. So before we start drawing all the things, let's also find the null finds just to be complete about it. So the null finds, we just set each of our derivatives equal to 0. Right? Again, I should really be emphatic about it. When you're finding the null finds, you're finding the line of no change. Null, nothing, no change. So to find the null finds, you're just setting dx dt equal to 0 or dy dt equal to 0. I do want to think of it as an or because they don't both have to be 0 at the same time. They're each independent 0. In fact, I should say, when they're both equal to 0 at the same time is when you have an equilibrium, which is at the point 0, 0. That becomes more important later when we talk about non-linear differential equations, which I think we will talk. I hope we'll talk about. Yeah, we got still like 5 weeks left. We should be able to talk about that. So let me ask you all. Write down the equation for dx dt. So if I'm setting this equal to 0, I'm really setting what equal to 0. You should be able to get that from the matrix. Totally. saying 6x minus 2y equal to 0. I'm typically solving this for y when I do it. So 6x equals 2y, y equals 3x. So that's my x null line, meaning along this line, all of my arrows should be pointing which way? Vertically or horizontally? I'm saying there's no change in what? In x. So they should be up and down. So they should be vertical. It wouldn't be wrong. I'm just better at graphing when I know it's y equals something as a function of x. I know how to graph the line y equals 3x better than I know how to graph the line x equals 1/3 times y. So not wrong, just usually we are kind of trained to do things in terms of x because we've been doing it that way for most of our mathematical lives. So I would always encourage you, if you can, solve for y in terms of x, or if you're doing x1 and x2, isolate x2 in terms of x1, because x2 is like your y. Same deal here. If I set dy dt equal to 0, are these going to be the same? No, they're not. Okay. I've got 3x plus 1y equal to 0. So y is going to equal negative 3x. I was going to be unhappy if there. Well, 3x plus 1y. I think. Okay. Right. The matrix is 6, negative 2. So again, right, this matrix, that matrix corresponds to these differential equations. dx dt equals 6x minus 2y, and dy dt equals 3x plus y, or plus 1y. Do be careful when if you're given these equations, make sure that if you're missing a variable that you write them in order. Like if you're missing an x, you should get a 0 in that part of the matrix, or missing a y, you should get a 0 in that part of the matrix. Cool. And so for this one, our arrows should be horizontal. Okay, so now we're going to do our best to draw this thing. They're not really partial derivatives though, I mean, you're not wrong to make that analogy. They're not really partial derivatives though, because we don't have a function of two variables. We're saying that we have these differential equations that both depend on these other functions, but everything here kind of is a function of time. That said, you could totally make an analogy that so we didn't do a lot of this, but when we were finding like the critical points of a function of two variables, we were setting the partial with respect to y equal to 0 and the partial with respect to x equal to 0 and finding the points that satisfied both those equations. The same thing is kind of true here. If you set this derivative equal to 0 and this derivative equal to 0 and find the points that satisfy both equations at once, which is only the origin, because these two lines that go through the origin are only going to cross at the origin, then you're kind of finding like the critical point. So it's a similar-ish idea, but not exactly the same. So then if we're going to try to draw this thing, what do we got here? So let's see, I'm going to do my null lines. I'm trying to use good colors here. So let's see, I've got my, oops, yeah, it's going to be it's going to be a little tight. So here's my eigenvector for 1, 1. I'm going to draw a little shy of the slope 1, 1 just to give myself some room to work with here. So here's my eigenvector or my eigenline for lambda 1 equal to 4. So I know my arrows are pointing out because it's a positive eigenvalue. Oops, can't see all that. And then for my other eigenvalue, the eigenvector was 2, 3. So I'm really just going to go over 2 and up 3. So let's do that one in red. So, and then this is where I'm trying not to be super specific because I want to give myself some room. Over 2, up 3, and then the other one's over 1, up 3. It's gonna be a little dicey here. Let's say that seems potentially reasonable. Sure. Let's do that. So here's my other eigenvalue, eigenline, where the lambda was equal to 3. And so again, we're pointing out. The eigenlines are the only lines of travel that point directly away or directly towards the origin. Any other place you start, you're going to curve in some way. So, oh, now we need the nullifyings. So the nullifyings are y equals 3x and y equals negative 3x. So they're kind of steep. I'm drawing both in black. Sure. I want to give myself a little room to work with here. So there's my eigenline, y equals 3x. So that's my y equals 3x, where dx dt equals 0. So all my lines are vertical. And it's a pretty safe bet that they're all pointing upwards over here. They're all pointing downwards over here because of what they're close to. Oops, you can't say that real. Sorry. Got that. And then finally, the last one, y equal to negative 3x, which is over here. It's the kind of the mirror image of that. dy dt equals 0. Y equals negative 3x here. Now they're all pointing horizontally. So I'm like this. And looking at what's happening nearby, I'm guessing they're going to point to the right over here. Although I might want to check. If I really want to check, I've got my equation, dx dt equal to 6x minus 2y, and dy dt equal to 3x plus y. If I pick a point on this line, like 1, negative 3, plug it in here, 6 plus 6 is 12, which is positive. So I would be pointing to the right. Okay, so now the question. If we start somewhere else, like if you start, I don't want to say this the right way. If I were going to start maybe like, okay, be careful. If I was going to start maybe here, I know I'm going away from the origin, right? Because we are unstable. So if I'm going to be getting pushed upward and leftward. So I'm going to kind of go like, oops, like that. Like that. I might end up turning around and going like, sorry, I should have crossed this more horizontally. Probably like that. Because I was going upward and left, but then I crossed this thing and started going down and left. You don't get your asymptotic behavior so much because the asymptotic behavior really would be if you went backwards towards the origin. Like that. So if we start here, we end up going away like that. Or if you were to start, I don't know, somewhere like here, you're getting pushed right and up, and there's no real nullifying the cross. So we're just going to kind of get closer like that to that. It's kind of funky. Like here, good question. You do, but the eigenvalue that's bigger is stronger. So I believe we end up going like that towards the one that's bigger. Now, what's great about this is we can actually take a look. Let's take a look at the graph for real. So let's see, our equations were dx dt equal to 6 times x minus 2 times y. And 3 times x plus 1 times y. Or just y. There we go. Oops, come on. And so, right, like if I pick a point between the line y equals x and y equals 3/2 x, which is maybe like, so maybe like here. You can't see it very well. You can't see the thing I was saying, which is unfortunate. So it looks like what I'm saying was a lie if you look at it that way. I guess it's hard to see without more scale. On the other hand, if we start somewhere over here, like we did, look, it does the thing I said. I wasn't lying, or I knew what I was talking about. But here, so here's the thing I want to point out that I did say that is worth noting. I mean, so I started this way and I was going up and left because I was in the section where kind of on the other side of it. And then when I get to this null line here, I really should be crossing it purely horizontally, because that's the only way you can cross a null line, is purely horizontally or purely vertically. So I'm crossing it horizontally, and then after, if I was going up and then I was flat, I have to be going down after that. If you cross a horizontal null line, you change from up to down. If you cross a vertical null line, you change from left to right. So yeah, that's not a good example. Yeah. Okay. You guys are asking really apt questions. I think you're being very thoughtful about what you were saying. Are there questions about what we have said or done here, particularly? Oh, I know. I have something I will say though. Give me a second. Okay, look at that for a second. I wish, you know what I wish this had, which it doesn't, which is too bad. So there is something you can download, which is really cool, that has like a lot of extra features. Like some of these things, if you play with them, they will actually let you also graph the eigenlines and the null lines, which is kind of cool. You can't really do that here, unfortunately. I'm curious about something though. What if we go really negative? Can I go that negative? Let's find out. Oh yeah, it's super negative. So now like, but look at what happens when we go way out that way. It just keeps going down to the left. But right, notably, it is not spiraling around because we can't cross an eigenline. So that this eigenline here can't be crossed. Kind of neat. Let's keep going down to the left.
So for spirals, do the eigenlines get?
There are eigenlines with the spirals, or the thing is, there are eigenvectors, but they don't make graphical sense because they're imaginary. So that's what all this kind of was really in response to, the fact that for real eigenvalues, we have real eigenvectors and eigenlines that we can graph. Whereas for imaginary eigenvalues, there are imaginary eigenvectors, but we can't really graph them. So there isn't a barrier, which is why we get this spiraling kind of effect. We can keep just going around and around and around ourselves. It's also because of the oscillatory nature of the whole e to the I theta equaling I cosine theta plus I sine theta deal. And you're going back and forth, back and forth, back and forth. Here, we're not getting that. We're just getting, right, what we've got here is, right, we've got some general solution where x of t is equal to c1 e to the lambda 1, which was 4, times v1. I should really just do the first part here. Sorry, 1 second. v1, which the x component was 1, plus c2 e to the lambda 2t times the x component of the second one, which was 2. And y of t is equal to c1 e to the lambda 1t times the y component of the first eigenvector, and c2 e to the lambda 2t times the y component of the second vector. So we are graphing x of t, or I should say we're graphing y of t versus x of t. So there is no t on this graph. But what we're saying is, if you start at some initial condition, so I'm pretending like here I started at maybe something above that. So maybe I had the initial condition where at time equals 0, x of 0 was 1 and y of 0 was 4. And so then I can actually find the initial conditions. I guess I'll do it. Maybe I can find the t values. So plugging those in real quickly here, I've got, let's see. So x of t is 1 when t is 0. So I'm going to have that equal to c1 plus 2c2. And y of t is 4 when t is 0. So that's going to be c1 plus 3c2. Right, because the e to the t part 0. And then so subtracting these, 1 minus 4 is -3, 0. 2 minus 3 is -1 ct. So c2. c2 is equal to 3. And then c1 is going to be 1 minus 6, which is -5. So then what we get is that x of t, starting at this point here, our particular solution, which is this curve here, is x of t equal to, let's see, c1 was -5, so -5 e to the 4t plus 2 times 3 is 6 e to the 3t, and y of t is c1 is -5 e to the 4t, c2 is 3, so 9 e to the 3t. So what we're saying is, as time goes on, right, you're going to get really negative numbers and really positive numbers. But since this power is bigger than that power, this is the dominant term. And x ends up becoming really, 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 really negative as we go further through the book. Similarly, since this power is bigger here, this is the dominant term, and the y values also eventually get negative, negative, negative. They start off getting going more positive at first, but then we turn around and go. That's kind of cool. Yeah, I think that's the right name. Yeah.
What is wrong when it's this only this?
What do you call that? You call that the? It might be. That might be the right word. I think that's it. And then I remember. Oh, I did. Yeah. Let's take a look. I feel like I look in the book real quick just to see. I unfortunately, admittedly, I'm slightly bad with the names of things in this particular section. And I know they talk about it in the book real quickly here. So null client eigenvectors, right here. So this thing here. Part A, plus the phase plane with null clients in purple, blah, 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 blah. The red curve is the solution to the initial value problem, and its components are plotting it. So I guess this here is the plot of the components, x2 of t and x1 of t versus time. But I feel like that's, I mean, I guess the trajectory is really this thing here. These are just the individual components of the trajectory. Right, so this is t, and this is either your x1 or your x2, depending on what you graph. Yeah, we often graph both at the same time. Sure, yeah. So that's only a thing that we encounter if we are having a fire, which none of these have been so far. So for this one, I will fully admit I'm not great at graphing the trajectories, but the thing is they're not too hard to graph. So if we look back at this, for example, so you really kind of have to have a particular solution to graph the trajectories, right? Because if you don't know where you're starting at, you can't really graph the thing. So we said we were starting at the point x comma y equals 1 comma 4. And so if we just look at our graph for a second, look what's going to happen. If I start at the point 1 comma 4, so if I follow this trajectory, what's happening to the x values as I move from here along my path? Do they get bigger and then get smaller, or do they immediately just get smaller or immediately just get bigger? I feel like you could argue that they don't get bigger at all. Right, from this point here, am I moving right to the right at all, or am I moving only left? Only left. So from this point here, my x values are just going to get smaller and smaller and smaller. So trajectory wise, what we have here is the x of t component is starting at a value of 1 and then just getting super duper negative. Actually, I suppose I've graphed that kind of wrong. No, I guess it should probably look more like an exponential function. I've drawn it not quite like that. It's probably actually look more like this. That would be x of t. Right. The problem is this seems to be slowing down. It's gradually, it's not getting negative very fast. Whereas the thing is exponential. The thing is totally getting negative fast, meaning it should be going like that. So it gets super negative very quickly. And then the y of t's are going to be similar, except, so this is x of t, which is equal to, we had negative 5 e to the 4t plus 6 e to the 3t. And the y of t's are going to be similar, except they're starting up a little higher at 4. But they're going to do the same sort of thing. They're going to go down, 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 down. And they're probably going to, I can't tell which one's bigger. They might cross, they might not. Oh yeah, in fact, I should argue it goes up a little bit because it certainly does. Y gets bigger a little bit, maybe goes up to, I don't know, a little bit higher. Oh, yep. And so then it's going to maybe something like that. And what I would encourage, I know, right? This is all like very organized looking. What I would encourage you to do is to look at the graphs of each of these things on Desmos, because looking at them will actually help you see they should look similar to this, but they might look more precise if you look on Desmos. So that's what I would do. But that's what's happening with these trajectories here. So we're using, right, this graph, like you said, Erica, right? When we go from here onward, we're going purely left, but we're not going purely down. We're going up a little bit first and then down, 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 down. Yeah. All right, we're out of time.